with very high quality. You can also have roll-to-roll processes of 100 micron thick glass with nanometer level roughness. So you can make these things in very, very high volume. You can eliminate grinding and polishing. So a lot of opportunities to really make cost-effective processes using glass. And again, for the same reasons, it's a very scalable material. So if glass is so good, how come it hasn't been taken over the mainstream? So there's been a lot of challenges, and so this is where I've spent my last decade is, if you want a 200 micron or thinner piece of glass, the challenge has been how do you introduce that into the supply chain? So you have a couple of issues. So you can see from this picture, I think this is an 8-inch wafer, maybe 75 microns thick, but far too much gravity sag to process in a semiconductor environment, right? Not only would your sensors be going crazy, but you'd literally be running into things just because there's too much deflection in the glass. And also, there have been a lot of people working on metallization of through glass vias. And the challenge has been it hasn't been any standard approach. There's been multiple approaches, and it's been paste, there's been plating, fully filled plating, conformal plating, and really haven't achieved a mainstream approach to do the via fill technology. So that's also been a challenge for adoption for TGV applications. And so what Mosaic is doing, and this is our core technology, is we have a temporary bonding technology where we could take a glass or a silicon handle, but primarily we'll use a silicon handle wafer, apply a very thin layer that we call ViaFirm. So it's the ViaFirm bonding technology. And so you apply that to the handle, and then you bond the thin glass to the silicon handle wafer. And it's a submicron layer, and it's very clean and very uniform, and it's a room temperature bond. So you basically put the wafers in contact, and it sort of self-propagates to establish that temporary bond. So one way to think about this is it's kind of like a van der Waals bond, but if you have a van der Waals bond and put it in the oven to 200 to 50 to 300 degrees C, it becomes a permanent bond. You'll never remove it. With this approach, you can go up to 450 degrees Celsius, and it doesn't outgas, and it still remains temporary. So it really gives a very attractive way to process the thin glass like it's a silicon wafer, and allows you to leverage the existing supply chain to process thin glass. So the whole idea of this approach is make the thin glass look as much like a silicon wafer as possible to really eliminate the barriers to entry for high volume manufacture of glass substrates. So the carrier, not only does it address the flatness, right? So now you have the stiffness of the silicon wafer. The equipment interface is a silicon wafer, so all the sensors that are embedded into the volume equipment that are used to sensing silicon will still be sensing silicon. And the physical interface to the vacuum chuck or the electrostatic chuck is a silicon wafer, so much less concern about putting multi-component glasses up against the equipment. So really addresses a number of these barriers to entry for glass. High-level view of the approach. So as I mentioned, you could have glass with or without vias. They're essentially manufactured before bonding. You apply what we loosely call an adhesive to the handle wafer, and then you put those in contact and they bond. Then you process the wafer, and then it's a mechanical debond. So the cartoon on the left is showing the debond process. It's a room temperature debond. There's no laser separation, no chemicals, no high temperature. You essentially initiate the debond near the perimeter, and then it's a mechanical peel to remove the wafer. Generally, we'll put the thin device wafer down on dicing tape and peel away the thicker handle wafer. So this cartoon is showing a glass handle wafer just so that you can see the debond front through the glass. But once you initiate that debond, it's really a well-controlled mechanical peel to remove the handle wafer. So some very important characteristics of this temporary bond. It's a very thin inorganic layer, so it's very resistant to higher temperatures and harsh chemistries. So we process our wafers with HF, with SC1, SC2 cleaning. Again, you can go to 450 degrees C, even higher, and you don't have any outgassing. So it's a very attractive for introducing with standard semiconductor processes. The other important thing is it's very thin. It's not a 25 or 50 micron thick organic adhesive. It's a very thin submicron layer. That's important for a couple of reasons. One, it allows you to maintain good flatness and planarity for your lithography steps, for example, and gives you the opportunity to go to finer line and spacing. There's other important implications where you can enable very thin fused silica products. So while display glasses can be manufactured in 100 microns thick or thinner, fused silica is manufactured much more like silicon. So you have more of a boule, a wire saw, and a grind and polish process. That makes it very difficult to get below 300 microns. But by leveraging our very thin temporary bond, you get very good total thickness variation of the bond, and you don't have to worry about managing flatness. And so you can bond a fused silica wafer and grind and polish it to, below 200 microns. We've gone as low as 70 microns, and get very good TTV in flatness using that approach. It's much harder to manage that using a thicker, spin-coated adhesive. So a lot of advantages for using this thin inorganic layer for enabling new technologies in existing processes. So I think I've already talked enough about this stuff. A couple things I hadn't mentioned yet. So the bond energy is on the order of 400 millijoules per meter squared. So if that doesn't mean anything to you, it's about 2 times a typical van der Waals bond. But that bond energy can be tailored. So we ended up at 400 as a standard because that was strong enough for processing like CMP and grinding, and weak enough to do an easy debond. But we've had a customer who wanted to put a very thick coating on the device wafer, use our handle to support it during debond, and that standard bond energy wasn't quite enough to maintain a good, it didn't pop off, but it didn't maintain a good full bond. So we were able to dial in a bond energy that was 2 times the standard level, and it worked very well to enable a very thick coating to be processed on a 100 micron thick piece of glass in an 8-inch format. So that tailorability can be important depending on what you're trying to do with the thin glass and what your downstream processes are. So if you want an easy debond for the next step, you can tailor that bond energy lower. If you want to put a very high stress coating on, you can ramp up that bond energy and get a little bit more stronger force holding that wafer down to the handle. So that can be a very important aspect as well. And again, by and large, we've shown to be very compatible with existing PVD, CVD, etching, cleaning, CMP. We haven't had a single issue at CMP with any debond. We've had very good results with CMP of the copper layer, but also of smoothing the glass and thinning the glass. So it's very robust in shear and a little weaker in tension, which allows for the debond. Another important aspect, so a lot of people wonder what's the surface of the glass after debond. And so what we did is we took a couple of wafers or a couple of process sets, 2 different cleaning processes, And so the wafers were cleaned, and then one surface was bonded to each wafer. And then we debonded it and did an XPS of each surface. So what the intent is, the top surface that didn't touch the handle wafer is sort of an as cleaned surface. And then the debonded wafer would be, if there was any contamination, it would be the contamination from the bond layer. But what we're seeing, and so what I'm showing here in the plot in the bottom right is the difference between the bonded layer and the debonded layer. And basically, the only difference you're seeing is in the carbon and the oxygen. The carbon, we believe, is adventitious carbon, and then the oxygen could be related to some of the processing. Oxygen gets a little bit depleted on the surface. But by and large, you're not seeing any contamination whatsoever from these other components. So it's a and nothing was done in between the debond and the XPS measurement. So there wasn't any cleaning or polishing. So it's a very, very clean bond surface that really allows good integration for flipping the wafer and then doing backside metallization, for example. And then in terms of process scalability, so in-house at Mosaic, we have the ability to go up to 300 millimeters today. Early on, the majority of the work's been at 100 to 200 millimeter, but we do have 300 millimeter capability already. The technology itself was developed for flexible panels, so it can be scaled up to Gen 4 or higher panel size. Mosaic doesn't have that capability, but the general process is scalable to panel level. And so that would of course be on the roadmap, you know, pending industry motivation. So, you know, how does this really enable via metallization? So I spent a lot of years trying to optimize how you fill vias in glass. So a lot of times the through glass vias are hourglass shaped just because the nature of the laser and etch process, which is a pretty standard approach for glass. And what Mosaic does is we take pains to not have an hourglass shape, but to have a more tapered via to make it look like a blind via in TSV, for example. So, you know, for hourglass, people have tried conformal coating. That's good enough for some applications, but then you can't do a stacked via. So people don't like an open via. So they want a fully filled via. If you need a fully filled hourglass, you're really limited to 3-to-1 aspect ratio or smaller, and you tend to want smaller vias. So that gives pretty rigid design rules. And then there are paste solutions, but a lot of, if you have a low temperature paste, you tend to have issues with conductivity and perhaps outgassing. High temperature paste tend to have a high sintering temperature, and so then the CTE mismatches cause an issue. So all of these things have been done over the past decade, and what we're trying to do is make this look like a silicon wafer as much as possible, so that we can leverage wafer level metallization strategies to really enable high volume capability. So we put a tapered via in the glass and then bond that to the handle wafer. And what that does is it makes it look like a blind via in silicon. And today we limit ourselves to a 35 micron diameter via and smaller. So that makes the via fill process faster and less expensive. And it also eliminates the CTE question. So if you have very large vias, then you start to have to worry about the CTE mismatch between the glass and the copper. So by getting a tapered via and having it relatively small, you keep the cost down and you maintain high reliability design rules. Then you would take that via in step B and you do, for example, a PVD adhesion and seed layer. Often it's titanium and copper, and then you do a bottom-up fill to fill those vias. And then from C to D, you might try to use that first metal layer and just pattern it to use it as your first metal layer, or you CMP that off and deposit your first metal layer. And then step D could be, 4 steps where you put your dielectric and then another metal layer, et cetera. So you do that front surface buildup, and then if you need to metallize the backside, then you would probably use a more standard 3M or Brewer Science adhesive to bond to that top surface, debond the initial handle, and then do the backside metallization. One of the main reasons why you'd use the more standard temporary bond technology on the top surface is since our layer is so thin, once you add topography or roughness to that surface, it's much harder to do the bond. So you'd want the forgiveness of the organic adhesive to do the backside metal. If you're doing a Damascene type approach, we believe we could use our process for the backside, but that hasn't been done yet. But basically, if you have a good, smooth, flat surface, we can bond to it. So that's a very high-level flow of how you'd leverage our technology to enable thin glass, and then ultimately you'd debond and have your device. Here's just some examples of us doing what I just described. So the top picture is showing a 100 micron thick glass wafer on a silicon handle after PVD seed and bottom-up plating. This is a 30 micron via and 100 micron stick. I think this was a 6-inch wafer. And then the second picture is showing a cross-section of those vias. So you can see an important aspect here is that these are fully filled vias. So if you have voids in those vias, that's actually been the reason for a lot of failures for previous work in glass. If you don't do the via fill properly and you have voids and you raise the temperature, the voids in that copper expand much more than in the glass or the metal, and that causes cracking. By avoiding the voids, I've done quite a bit of work with ITRI and Georgia Tech and Micros. If you avoid the voids, you can get very good reliability. So we've passed HASS testing, thermal cycle testing, drop testing, but it's really important to not have voids in that copper. And again, by mimicking TSV type vias, you really improve your ability to avoid those voids. And then the bottom picture is showing, the next to the bottom picture is the wafer after CMP. So you can see in the top 2 pictures is about a 4 micron overburden of copper after plating, and then we CMP'd that off, and we've had very good success with Axis technology and also Intrepix in Phoenix for doing the polishing of these wafers. And then we annealed these wafers to 400 degrees C, and again, you don't see any cracking around the via. We inspected every single via on this wafer, and there was no cracking that you would see if there were voids. So a very good demonstration of, sort of interfacing with the processes needed to enable thin glass devices. And then here's another important aspect of this process. So we took one of these wafers and then debonded the wafer and looked at the back side. So I just showed you the top side. After debond, we looked at the planarity of the via on the back side to see how good of a fill we got just by leveraging a very good interface between the glass and the silicon. And on the right, you see this is a Zygo white light interferometer, basically looking at the planarity of the copper and the glass surface. And without any polishing, you're better than 100 nanometers planarity on that back surface. So again, by having a very thin layer, if you had a wet adhesive, that would wick up into the via and you would not get a good fill. But by having this very good interface, you get very nice planar and uniform via interface without any polishing. So I will say that when you do an anneal, so what I'm showing here on the bottom right is the planarity after a 260 degrees C anneal. You do see a little bit of a piston, about a quarter of a micron, so 250 nanometers. So that would need to be managed depending on your application, but still that would be a very quick planarization if you need better than 250 nanometers. But the other aspect of this is we wanted to measure hermeticity. So we annealed these wafers up to 260 degrees C and did it. So we did the process I just described. So the bottom up fill, CMP to remove the overburden, mechanical debond. Then we did the anneal, and then we measured 9 regions on that wafer for hermetic performance. So first we did the gross leak red dye test, and then we did a helium leak test. 8 of the 9 regions had better than 10 to the minus 9 atmospheres cc per second of helium. And after the anneal, we still see the same performance. So the main outcome here is that you can get hermetic, helium leak hermetic performance by leveraging these standard plating processes. And that's pretty important for a number of MEMS and other applications that are interested in using glass as a lid or an interposer. That hermetic performance is really important to protect those sensitive structures underneath. Now I'm gonna, so Ermi, I don't know if you want to pause for questions or just keep going.
We can take some questions if you prefer right now, because you're going to move into a slightly different area right now, right?
Yeah.
Okay, so yeah, please put in your question in the chat. And by the way, I apologize because I didn't start the recording in the very beginning. I completely skipped my mind. But I'm going to go through the questions from the chat in the order they came in. So in terms of the slides, yes, slides will be sent to everybody, and hopefully the recording, which only starts about 10 minutes late. The first question is the adhesive liquid and spin coated?
No, this is it's more of a deposited type adhesive layer. It's not spin coat.
Okay, thanks. The next question is from Daniel Fu. After debond goes back to very thin and flexible state, won't fine circuitry and vias be a problem from cracking or peeling in handling?
So generally no, but what we do is we'll debond it to either dicing tape if you're heading off to singulation, or you'd bond it to another wafer. So in that case, the flatness will be maintained before debond. But in the other case, you put the dicing ring down on the vacuum chuck, it stays flat, and then the handle wafer is deformed. So you do maintain flatness. And then once it's diced, the features are so small, it's actually quite stiff. So I think that can all be managed.
And if I may add, I mean, this is very similar to from the thickness perspective to background ground silicon wafer also, right? I mean, you're using the similar technology in terms of transferring to dicing tape or a film frame / dicing tray, right?
Exactly.
You're using the same infrastructure.
Yep.
Yes, thank you. The next question is from Aric Schlaffer. His question is, the TGV, is it made by laser or mechanical drilling?
Yeah, our TGV is made with a laser-based process.
Okay, thank you. And I think, as Aric mentioned, there are some other technologies that use combination of laser and etch, right, Aric?
Yeah, we also have an etch step. Yeah.
Okay. Next question is from Raj Gupta. What are the specs on the surface roughness after CMP and along the sidewalls of the vias?
So after CMP, it's generally less than 1 nanometer is what we've been specifying, and that hasn't been an issue. Along the sidewalls, the only thing I could do is I don't have a good measurement of the roughness, but it's a very smooth via. You can get some idea from these profiles, but it's I don't know that it's sub nanometer, but it's a very smooth. It's not rough and like a PCB type via would be. I don't know if I have a better image, but anyway, this gives some idea of the smoothness. But that's maybe something we could take a closer look at if it's important. But it is certainly sub-micron.
Yeah, okay. From Robin Taylor, for annealing, do you have a temperature ramp up and ramp up specification to avoid glass cracking?
We so we have a ramp rate that we use, and it's actually the cooling rate's probably as important or more important as the heating ramp, but we do have a ramp rate that we use and could share.
You have a profile that you can share. Okay.
Yeah.
Okay. Thank you. From Roger Massey, what's the capability in terms of fully filled TGV diameter and depth?
So right now, the most mature capability is 3-to-1 aspect ratio, so 30 micron via, 100 micron stick. But we know that we can make vias 15 micron diameter, 100 micron stick, and we're also working on or demonstrated 30 micron via in almost 200 micron stick. So we know that these can be filled. I don't have as much data for the latter two, but we think 3-to-1 to 6-to-1 aspect ratio is where we're going to be playing.
Okay. Okay. David Citrin, what about 6G? I'm not sure what that question means. In terms of requirements?
It doesn't mean much. I just want to see a response,
Okay.
see what the future holds.
Okay. What does the future hold, Aric?
Well, what I can tell you is that we've got some government funding to enable terahertz level communications with glass. So the glass-based solutions actually are very, the higher in the frequency, they actually become even more attractive. So I think 6G is even more or just as appropriate for glass as 5G.
Yeah.
Thanks. I'm sending you an email.
Okay.
If it sounds interesting, let me know.
Yep. All right. Thank you.
Okay. Oliver Kirsch, what type of glass is typically used specifically regarding hermetic issues?
Yeah, so that's a good question. I can tell you our base glasses are fused silica and Corning's Willow glass. We can also work with Asahi's fused silica and their display glass. We've certainly done some work with Schott's AF32 glass. So the easy answer is fused silica, and the CTE matching glasses are sort of the base materials that we work with. In terms of hermeticity, we are seeing that so far we can anneal the SG3 or the CTE matching silicon glasses to 400 degrees C without an issue. For the fused silica, it's got that another 2.5 or 5x lower CTE. We're not seeing cracking, but we're not achieving hermeticity. We achieve hermeticity up to 260 degrees C. There's some work to do to get to 400 degrees C. So we don't think it's a fundamental issue. But in terms of answering your question about hermeticity, I don't think it's an issue for the higher CTE glasses. There may be a little work to get there if you have to go to high temperature for the low CTE fused silica. I hope that made sense.
Okay, I hope to, but I need to move on. There's lots of questions. How much more time do you have of your in your presentation, Aric?
Maybe 10 minutes or 5.
Okay.
Yeah.
Okay, let's go through the questions. There's a lot of questions. So from Paul Hale, did the zygos surface planarity measurement take into account the differing reflectances of the glass and copper? If not, the planarity may be even better. That's his comment.
So I do know that the operator did do some things to take that into account, but it's a very good point. Yeah, that's a very good point. We don't have a mechanical measurement. We believe what we measured, but you're right. The reflectance differences can have an impact.
Thank you, Paul. Minwoo Lee, how to make vias before bonding, laser or selective laser induced etch? Yeah, he already answered the question, but you can also answer it again.
Yeah, it's a laser and an etch process. Yeah.
Yeah. Ron, is that Ron Humiller? I don't know. You list VIA and RDL as lower cost than silicon. Can you elaborate more on your analysis?
Yeah, so I think in that case, that's a very good question because we're trying to use the same processes. I think in that case, it's more related to the elimination of back grinding. So by leveraging thin glass, you can avoid back grind and polish. And we're actually seeing in some very specific applications that can be very impactful. And it's not only cost, but reliability. Yeah. Sorry, go ahead.
I was going to say, yeah, that was your buddy, Ron Humiller.
Okay.
Whose buddy, mine or Eric's? Anyway, sorry. Next question is from Jack Chen. What is the copper to glass adhesion force, for example, peeling strength?
Yeah, I don't have that number, but that's the whole purpose of the titanium or the titungsten layer is it does give you a very good adhesion force. And all I can tell you is we've made some wafers for a customer and they bonded things to them and we're very, very pleased with the adhesion strength. But unfortunately, I don't have a good number to give you today.
Okay. Minwoo Lee, what kind of laser do you use for the vias?
It's a top secret laser. So,
that was what I was suspecting.
Yeah, maybe at some point in the future I can share that, but I'm not comfortable doing it today.
Yeah, not yet. Okay, a question from Raj Gupta. Can via firm be used to bond to other substrates such as alumina, metallized surfaces on top of alumina?
That's a very good question. So generally the answer is if you have a well-polished, low roughness surface, so let's say less than 1 nanometer or maybe less than 3/4 of a nanometer roughness, we can bond to it. So we've bonded to silicon carbide, silicon, quartz, sapphire. But if the roughness gets higher than a nanometer, then the bond gets much more difficult or impossible. So for example, a polycrystalline material is very unlikely to bond without some smooth layer on top of it.
Okay, that's actually very interesting. Question from Yohua Chen. Wow, you're up at this late. Do you have plan to enlarge the size to 500 millimeter by 500 millimeter? That's YA Chen from Unimicron.
Yeah, by the way, it's nice to hear some of these names again. So it's
I know, me too.
So I certainly have a plan to do it in the roadmap, but I think the industry will dictate when that happens. So we're not planning to preemptively buy that equipment, but it for sure is relevant, and for the right opportunity, we would entertain that.
Okay, very good. That was a very active chat session. So I would like to let Aric finish his presentation, and then if there are further questions, we can do it at the end of his use cases section.
Yep. Okay, well, thank you and appreciate the questions. So now I just want to step through some, I say that we can interface well with the supply chain. I just want to step through some examples of this, some things that we've done over the past couple of years. This first one is, it turns out it was a photonic application, but the customer wanted 100 micron thick glass with a 1.8 or 1.7 micron thick nickel gold structure, 4 structures, so it was a multi-project wafer, and down to about a 6 micron feature size. And so we worked with Micros in Raleigh-Durham for this, and this was one of our early processes. But what's really exciting about this one is we bonded, 8 or 10 100 micron thick glass wafers to a silicon handle, gave it to Micros. They did a little bit of development on the lithography optimization, but came out with very nice features down to 6 microns. They plated 8 wafers. They did the litho on 8 wafers. We debonded 8 wafers, and then we diced 8 wafers. So we really didn't have any breakage processing these 100 micron thick wafers. Granted, they were 100 millimeter diameter, but still, no engineering development, just taking these wafers, putting them through plating and lithography and debond and dicing, and had very good success. So you can see images of the structures with good resolution, and then very good, this is also a Zygo, I think it's a Z-gauge instrument used to look at the feature size and shape. So this was a very nice example of being able to take thin glass, bond it to the handle, and then just really leverage existing processes. And then here's another example of some work that we're doing with General Electric. This is for a DoD application for an electronically steerable antenna in the Ka band. And GE was able to leverage our process to do 2 things that I've talked about. One was to thin the TGV wafers down to 150 micron. So they did this both in the willow glass and the fused silica. But for the fused silica, they were able to leverage our process to get the wafers down to 150 microns thick. And then they did the metallization. They put the structures on the wafer and then bonded 2 of the wafers together with thermal compression gold. And so we actually have, this work is ongoing through a phase 2 effort, a larger effort to actually make these steering antennas in the Ka band. But what's exciting here is the sort of incumbent process was on PCB, and the analysis shows that the lower loss of the willow glass will give 50% lower loss than the PCB, and that's really because of the roughness. And then the additional advantage of the loss tangent with fused silica will give you another 20% lower loss. So we think we'll see up to 70% lower loss on fused silica relative to PCB, which in this particular application, it's a battery-powered communications module. That 70% lower loss can be very important. In some similar efforts, we're leveraging the fused silica technology to do a 2-layer RF filter. And in this case, it's actually 7x to 30x reduction in package size. So by having the smoother glass, you can have much smaller features. You get the same electrical performance with a much smaller package size. And again, that's primarily due to the roughness. And so we're actively, this year, we have several contracts with the Air Force and the National Science Foundation, working with some folks perhaps on the call, to really make demonstrators for 5G filters, antenna structures for military, but certainly relevant for 5G, and then commercial filters for cell phone communications. So, and then we also have this terahertz interposer applications and also RF over fiber photonic interposer. So a lot of interest in applying this technology in various aspects of millimeter wave communications. And then another thing that we're doing, and maybe I won't take the time to go through a ton of details here, but we have a program that we've been working on with Fraunhofer. I think many people on this call know Ivan Endip, so we're working with his group, Fraunhofer IZM, And so what we're trying to do is design a thin glass-based patch antenna and compare it to the performance of a PCB patch antenna. And so what we did is we tried quite hard to match the properties of the glass and the PCB as much as possible. So with the glass, of course, we were motivated to be 200 microns or thinner. And so we tried to find a commercial PCB material that had similar properties, but that it was commercially available. So with those sort of constraints, here's the design parameters that we achieved. And I'm trying, I think it's a Megtron material, I think, the organic material that we're using. So here's the design. It's a 2x2 aperture coupled patch array. So it's, you know, the die is 15 millimeters aside. The structure is about 5.5 millimeters. And then what this is showing is the glass versus organic, the ability to get the bandwidth. So we're about 1.6 gigahertz bandwidth, the 10 dB bandwidth. So the glass was able to match the organic to achieve that bandwidth, which is important for, you know, the number of channels that you could potentially serve in this antenna. And then finally, these are simulations. We're currently fabricating the test devices, but we measure the actual gain performance over the frequency band of interest. So again, this is Ka band, and the glass is showing higher gain, higher peak gain, but also a much flatter profile over the entire bandwidth. So I think for the patch, it's not quite as pronounced as you see in the feed network, because the feed network, you could have up to a 2-inch conductor length, which has much more chances for lower losses. But even in the patch, we're seeing advantages for getting a flatter profile and higher peak gain. So again, this is all sort of packaged together, important work that we're doing this year. And these are all in process in fabrication, these devices. And I forgot I included this. So this is something it's sort of researchy, but actually quite interesting, and it's an active program that we're doing with the University of Florida. The idea here is to take low loss glass, fused silica, and University of Florida's low loss metaconductor technology, and apply them together to make ultra low loss, in this case, radar arrays. So the University of Florida has a copper cobalt metaconductor that basically reduces your conductor losses by 50%. And so we're looking to apply this into a glass-based technology for a radar array to make a very low loss compact radar array for autonomous vehicles, for example. And so just one example of results I wanted to show here is, as a demonstrator in a phase 1 effort, we applied this is a simulation, but you apply the technology for an inductor. So they modeled a 1-turn and a 2-turn inductor. The black dashed line shows a Q factor approaching a 100. And if you apply the metaconductor, you can get close to 200 Q factor. And then the 2-turn is not quite as high, but you can get, it's a 100x improvement at the design frequency, and you're over 100 of a Q factor of over 100. So we're currently working to actually make these devices as well. We've applied for phase 2, but this is also quite interesting way to leverage glass and this new metaconductor technology to have very, very low loss substrates. These are just one example of applications, but we think there could be broad application of this technology. So this is a little bit further out, but I thought it was very interesting to show some of the things we're working on. And then here's the design of a 2D and a 3D. So a 3D array just means 2 layers with the feed network on one layer and the patch on the other. And so again, we're working on making these demonstrators over the next year or so. And then finally, just a little bit conceptual, but again, it's something that we have activities in. How do you leverage this technology for really next generation packaging? And so we talked about this early on, but conceptually anyway, you could imagine taking a TGV wafer, attaching die to it, then taking a cavity wafer, leveraging our temporary bond technology and applying that layer to the TGV layer, and then coming in with another TGV wafer for a cap layer. And then you can end up with a embedded package device with electrical interconnects into the cavity. You could have optical sensors, sensitive optical sensors with electrical interconnect, and the whole thing could be hermetic. So the vias have been demonstrated to be hermetic. There's companies out there with glass-to-glass laser bonding technology that's demonstrated to be hermetic, and the whole package could be less than 300 microns. So again, it's a bit conceptual, but it's actually being worked on as we speak. So I think it's exciting for some of the things that we can do going forward to enable new structures and technologies. So again, very briefly, the industry trends over the past decade have they're really requiring new packaging solutions. Glass has been interesting for many years, but really the manufacturability hasn't been there. And this new ViaFirm technology really avoids a lot of the hurdles that have hindered glass adoption over the years. So we're really excited about the potential to really open up broad application for RF filters and antennas, MEMS packaging, and other hermetic designs, and then other sensing applications. So we certainly have a lot of interest in all of these areas, and our goal is really to unlock the value of glass going forward and really make it manufacturable. So thank you again for the opportunity, and if there's another question or two, I'd be happy to take it.
Yes, thank you very much. Lots and lots of very good information from Aric today. And thank you for that. We have a couple questions. I just want to be conscious of the time. We have a comment from Robin, an observation. He says, excellent progress and results. Nice to see and hear some well-known faces on here. Good luck going forward with the process. Yeah, I echo that. Thank you.
Thank you.
Follow-up question from Raj Gupta. He wants to know what are the specifications required for roughness in the mmWave type of requirements, applications?
So I don't have the hard number, but I think sub-nanometer or nanometer level will be preferred just because of the skin effect. So I'm trying to think. I think at 28 gigahertz, you're about half a micron, if I'm not mistaken, right?
Yeah, and there's a whole discussion. Yes, so it's so for the skin effect, the copper conductor or whatever the surface is really has to be very low nanometers, and that's a challenge always there for skin effect, right? So that's Aric is exactly correct. And then the last comment, question from Chudi at iTech. He wants to know, for the work with Ivan, do you have the simulated roughness parameters for the glass conductor interface or the Megtron or whatever dielectric conductor interface?
Yeah, actually the roughness wasn't included in the simulation. So we're actually quite excited to get the actual hardware fabricated and tested to see if there's further advantages there. My expectation is you don't see as much in the patch as you do in the feed, but it'd be great to see the data.
Yeah, agreed. Very, very interesting. Some of the case studies that you're working on. So it's just the top of the hour. I'd like to thank you all for attending. We thank Aric for the presentation. And look forward to working together. Again, just to put a little plug at the end, Aric's also providing us with for the iNEMI 5G project that some of you might be familiar with. We will be utilizing the fused silica wafers for looking at some of the standard reference material work that we are doing in collaboration with NIST. So that's another big, aspect of the project as we go towards helping 5G, 6G implementation into the industry. So with that, again, thank you all. Have a good day and rest of the day. And thanks very much. Thanks, Aric.
Thank you.
Yes,
Thank you.